Hello everyone, this is Dr. K. Purani, Assistant Professor of Mathematics, Arlimagu Palani and our Arts College for Women, Palani. In this lecture, let's see about connectedness related theorem in topology. Before going to theorem, let's see first let's see about two definitions. What is that? Okay, first definition is separation. A pair u of uv of subsets of a space X is called separation if these four conditions are satisfied. What is the conditions? U and V are non-empty and U and V are disjoint. Their union equals X. Fourth condition is U and V are open X. If these four conditions are satisfied, then we can say a pair UV of subsets of X is called separation. The next definition is a space X is said to be connected if there does not exist separation. Okay, what is the definition? A space X is said to be connected. If a space X is said to be connected, then separation does not exist. If separation does not exist means in these four conditions any one of the conditions fails. Okay, in these four conditions any one of the conditions fails. Okay, if a space X is not connected, okay, if a space is not connected, then separation exists. That means these four conditions are satisfied. Okay, okay, come to the theorem. The theorem, let A be a connected subspace of X if A is a subset of B is a subset of closure of A, then P is also connected space. See in this figure, X is a connected space. Okay, X is a connected space. X is a connected space. A closure is a connected. A is a connected subspace. We want to prove this B is also a connected subspace. Okay, so what is the hypothesis? Let A be a connected subspace and let A is a subset of B, which is a subset of A closure. We want to prove that B is a connected subspace. Okay, we prove this theorem by contradiction method. What is a contradiction? Suppose B is not connected. B is not connected. We just see in this definition if B is not connected means then there exists separation. There exists separation means what? Separation C and B, C and D of B. If separation exists means these four conditions are satisfied. What are the four conditions? C and D non-empty, C and D are disjoint, C union D equals B, and C and D are open in B. This is the four conditions of separation. Okay, we know that the hypothesis A is a connected subspace of B. So in the previous lecture, okay, sorry. In the previous lecture, we saw the theorem if the set C and D. Okay, sorry. If the set C and D form a separation, if Y is connected subspace of X, then Y lies entirely in C or Y lies entirely in D. That is, Y is a subset of C or Y is a subset of D. We use this theorem here. A is a connected subspace of B, so A is subset of C or A is a subset of D. Okay, suppose A is a subset of C means then C, it is the well-known result. Okay, it is a well-known result. If the point X in A closure, then U intersection A not equal to empty, where U is a open in X containing that point X, and A is a subset of X. This is the one result. Okay, already we proved. This is the one result. If X in A closure means then U intersection A not equal to empty. Okay, here this implies U intersection C not equal to empty because A is a subset of C, so we can write this. Okay, okay. This implies X belongs to C closure. So if X belongs to C closure means U intersection C not equal to empty. So what is the hypothesis? X in A closure, we proved X in C closure. So we can say A closure is a subset of C closure. Suppose A is a subset of C, then A closure is a subset of C closure. We use this result. By the result, A closure is a subset of C closure. What is the hypothesis? B is a subset of A closure. This implies B is a subset of A closure, which is a subset of C closure. This implies B is a subset of C closure. Okay, take intersection D on both sides. B intersection D is a subset of C closure intersection D. Note this as equation number 1. Since C comma D is a separation of B, okay, since C comma D is a separation of B, C closure intersection D equal to empty because of, say, okay, suppose C closure intersection D not equal to empty means what we get? Check. Okay. Suppose C closure intersection D வந்து not equal to empty. That is non-empty means see the result. Okay. What is the result? See. Okay. Suppose non-empty means their intersection is non-empty means what? Any one element is belongs to that. Okay. Let's see it belongs to C closure intersection D. If say X belongs to their intersection means we know that the result A closure equal to A union A dash. A dash is nothing. It is a derived set of A, that is set of all limit points of A. Okay. In the previous lecture, uh, we took what is A dash, what is the limit point definition. Okay. If you want to know the limit point definition means check my previous lecture. Okay. A closure equal to A union A dash. X belongs to C union C dash intersection D. We use the distributive law. This is the result. This implies C belongs to C dash intersection D. If X belongs to their intersection means X belongs to C dash and X belongs to D. Okay, X is a limit point of C and X belongs to C. If X belongs to derived set of B by the limit point definition, X is a limit point of C. Okay, we get the result what? We get the result C comma D does not form a separation, because if X is a limit point means C comma D does not form a separation. By using the theorem, if Y is a subspace, just in the previous video only we proved this theorem. Okay, just in the previous video we proved this theorem. But if Y is a subspace and AB form a separation means if and only if A dash intersection B equal to empty and A intersection B dash equal to empty. X is a limit point means of C, that is X intersection that is C dash intersection D not equal to empty. Okay, means CD does not form a separation. Okay, this is the contradiction for what? See, this is the contradiction to the hypothesis. See, which is the contradiction to the hypothesis. What is the hypothesis? C comma D form a separation, but we get C comma D does not form a separation. So therefore C closure intersection D are equal to empty, or C closure and D are disjoint. Okay, now I think you can understand why we here take C closure intersection D equal to empty. So we note this equation as 2. Okay, from by the equation we can write the first equation. What is the first equation? See, B intersection D is a subset of C closure intersection D. C closure intersection D equal to empty. So we can write B intersection D, which is a subset of D, by using equation number 2. We know that empty set is always subset of B intersection D. So we can write B intersection D equal to empty. Here C union D equal to B. This is the hypothesis. Okay. See the hypothesis. C union D equal to B. So we write, instead of B we can write C union D. We can use the distributive law. We get this. Okay. We get C intersection D equal to empty. We know that. So use this here. Empty union D is equal to, sorry, D intersection D equal to D, that is equal to empty. So D equal to empty. Okay, which is a contradiction. Which is a contradiction. This is a contradiction to hypothesis. What is the hypothesis? See, D is non-empty. This is the hypothesis. If suppose B is not connected means there exists separation. So these 4 conditions are satisfied. What is the hypothesis? D not equal to empty. So what we get, see, this is the hypothesis. So which is a contradiction. Our assumption, what is our assumption? B is not connected அப்படிங்கிற assumption is wrong. So therefore B is connected. Hence they prove. Thank you.